Hello everyone, welcome to mini courses. I'm Irene from the G11N SIG of the openEuler community. In this episode, I'm going to talk about the performance analysis method called top-down performance analysis. First of all, I'd like to ask you a question. Have you ever experienced the situation where your computer gets slower and slower over time? You might be wondering why this happens. From a technical perspective, the reason why your computer is slowing down is because it has encountered a performance bottleneck. To fix it, we need to figure out what the bottleneck is. Major performance bottlenecks of a computer include I/O, CPU, the memory bottlenecks. We can run the IO-stat, VM-stat, or SAR command to check whether there is an I/O bottleneck. However, it is less easy to identify a memory or CPU bottleneck. In this video, I will introduce the top-down performance analysis method, which may help you out. So, what is top-down performance analysis? Invented by Intel architect Ahmad Yassin, top-down analysis is a practical method for quickly identifying true bottlenecks in dynamic execution CPUs. It uses designated performance counters in a structured, hierarchical approach to quickly and correctly identify dominant performance bottlenecks. The idea is to drill down in the structured hierarchy, guiding us to right domain to investigate. Since I mentioned the drill down, you might be wondering, what is the start point? Modern dynamic execution CPUs have two main portions, a front end and a back end. The front end is responsible for fetching instructions from memory and translating them into micro-operations, which are then fed to the back end. The back end is responsible for scheduling, executing, and committing or retiring these micro-operations in the order of the original program. Therefore, to keep a machine balanced, the delivered micro-operations are usually buffered in some ready micro-operations queues for consumption by the back-end once ready. According to the micro-operation status, Ahmad Yassin designed a flowchart for a top-level breakdown. As shown in the flowchart, available pipeline slots are split into four basic categories: retiring, bad speculation, front-end bound, and back-end bound. For example, if a micro-operation is issued in a given cycle, it will eventually either get retired or cancelled, so it can be attributed to either retiring or bad speculation respectively. Otherwise, if a micro-operation is not successfully issued in a given cycle, it can be tagged based on whether there is a back-end stall. If there is a back-end stall, it can be attributed to back-end bound. Otherwise, it can be attributed to front-end bound. Because a superscalar CPU can issue multiple micro-operations per cycle, this classification is done at a granularity of pipeline slots. This allows the breakdown to be both accurate and robust, which is necessary at the top level of the hierarchy. With the top level determined, it is much easier to develop the entire hierarchy. Here is a top-down analysis hierarchy designed by Ahmad Yassin. Let's take a look at this figure. Each top-level category is split into two subcategories, and then more branches until the root courses. Next, I will explain the main concepts in detail. The first one is front-end bound. The front end represents the first portion of the pipeline where the branch predictor predicts the next address to fetch. Cache lines are fetched, parsed into instructions, and decoded into micro-operations that can be executed later by the back end. When the front end of the CPU undersupplies the back end, front-end bound occurs. In this hierarchy, the method further distinguishes between latency and bandwidth stalls under front-end bound. ITLB miss, iCache miss, and branch resteers are classified under fetch latency bound, while inefficiency in the instruction decoders is classified under fetch bandwidth bound. The second category is bad speculation. Bad speculation reflects slots wasted due to incorrect speculations. These include two portions: slots used to issue microoperations that do not eventually retire, and slots in which the issue pipeline is blocked due to recovery from earlier misspeculations. Ensuring a low rate of bad speculation not only improves utilization of available resources, but also increases confidence in metrics reported throughout the hierarchy. This method classifies the bad speculation slots into branch mispredict and machine clears. The first deals with how to make the program control flow friendlier to the branch predictor, and the latter points to other typical unexpected situations. The next category is retiring. The retiring category reflects slots utilized by good microoperations, that is, issued microoperations that eventually get retired. Ideally, we'd like to see all slots attributed to the retiring category. Nevertheless, a high retiring value does not mean there is no room for more performance. There are still at least 2 points of optimization that can be explored. First, microcode sequences such as a floating point assists hurt performance and can be avoided. And second, high proportion non-vectorized code can be optimized into vectorized code, because vectorized code can essentially let a single instruction or microoperation perform more operations and thus improve performance. The last top-level category, back-end bound, reflects the situation where no microoperations were issued due to lack of sufficient resources for accepting them in the back-end. Back-end bound is split into memory bound and core bound by breaking down back-end stalls based on execution unit's occupation at every cycle. For example, in a 4-wide machine, if 3 or less microoperations are executed in a steady state of some code, this would prevent it from achieving the optimal instructions per cycle IPC value of 4. These suboptimal cycles are called execution stalls. Execution stalls related to the memory subsystem account for memory bound. These stalls are usually caused by starvation of the execution units for a short period of time, such as when a load misses all caches. Core bound, on the other hand, is a bit trickier. Its stalls can either be caused by starvation of execution units for a short period of time, or due to suboptimal execution port utilization. That is, there is pressure on execution units or a lack of instruction-level parallelism in the program. For example, a long latency divide operation may cause serialization of execution, resulting in only a small number of execution ports being used in a cycle. Now that you have understood the key concepts, let's take a look at the hardware support used by the methodology to locate performance bottlenecks. The process might be simpler than you think. In this slide, I will briefly describe the hardware support required for a top-down analysis method. Modern CPUs contain a component called Performance Monitoring Unit, which provides a set of predetermined general-purpose hardware counters for calculating performance events. PMU events are used to measure performance metrics such as IPC, branch mispredictions, cache misses, and more. These metrics reflect information about the system's load, CPU utilization, memory usage, and so on. We can use such information to optimize the system performance. To enable top-down analysis, we only need to add 8 new performance events to a traditional PMU. Here list all top-down analysis-related events. Highlighted events are the new performance events. We have now reached the end of this course. In this video, I introduce the hierarchy, major concepts, and hardware support of the top-down performance analysis method. The approach itself is straightforward. Categorize micro-operation execution status at the top level first. With information provided by PMU events, some domains are flagged for possible investigation. Next, we can drill down into those flagged domains and can safely ignore all non-flagged domains. The process is repeated in a hierarchical manner until a specific performance issue is determined, or at least a small subset of candidate issues is identified for potential investigation. So if you are looking for a way to analyze and optimize the performance of your system, top-down performance analysis is a great choice. For more information about its technical implementation, see the link below. I hope you enjoyed today's course. See you next time.